And thank you everyone for coming. It's very nice to be here, not just by myself, so it's excellent to see you here. I didn't know that the bio was supposed to be used to introduce me, so the next slide is about what you just heard, but with a little bit of details, right? I'm going to talk about a journey. This is my journey. That's the way I interpreted the instructions I received when they told me, okay, it's your chance to show what you have done during your career. And that's what you will see on the slides now in a moment. And what I've done is and was to develop and take forward solutions for sustainability challenges. So these, they embrace different areas, not only CO2 utilization as I'm doing now. And I decided to pick up, like cherry pick, the best I've done. If I don't do it in this moment, there would be no other chance. And so I'm starting first with this slide. It is supposed to work like before. Just give me a moment. Academia and industry. The reason why I'm showing this is because I don't know if you know what a pinball is. I asked my son before coming here. We were in my office. He didn't know. I know what it is. It's that game that you press the buttons, the balls go everywhere. So my trajectory, my career is like a ball of a pinball. I've been going randomly everywhere to find my place, I have to be honest. But I'm going to simplify it here for you in moving between academia and industry. This is not working again. Not sure why. Apologies. Oh, there you go. Oh, here we go. So quickly, after completing this master, where unknowingly I started doing what I'm doing now, CO2 utilization, if you look at the top there. I worked on an experimental thesis on making carboxylic acid for pharmaceutical applications. So I was already working at the interface of academia and industry. I think this is going to be a bit difficult. Let's see. I moved to industry to work in this environmental management company. I worked there for a while, but I wasn't really extremely happy. So I kept looking around me it's not working. I believe I have to do it here. Is it the distance? Okay, I'll stay here then. I completed this master, the master that you heard before, a particular master in the interface of industry and academia. So that was run by Basel Polyolefins. Today, the name of this company is LyondellBasell. They are the largest licensors of polyolefin technology in the world. And at the time, I did this master in polymer materials at the Giulio Natta R&D Center. And I had the opportunity to work a lot with polymers, including going on pilot plants on their Spherizone technology. There, I've been, this to my surprise, I have to be honest, I won the first prize with the master thesis, including this beautiful medal that I have at home. It's a mixture of gold and silver. I don't know why to mix the two together. This gave me the opportunity to go to work for Basel Polyolefins. I've been offered the position, and I kept working there on trying to recycle polyolefins. You might not know what they are, but they are polyethylene and polypropylene. The two don't go very well together, although they are very similar. And I studied there on options to putting them together. And again, somehow something was boiling inside of me. That wasn't enough. I left, I went to the United States. It's not here, where I met my wife. And then I came back and I went to work in two other companies. The names are there, working with polymers again, PVC in Sovere and polymethyl methacrylate in this company, Tecres. And so I grew a lot of interest in working with polymers. Again, I thought, no, I need to do something else. I want to do more. I went on and I studied for a PhD. Probably the battery is off, I'm not sure. Okay. And I did a PhD where I combined all these things together. And from this PhD, I moved to United States back again to work on photovoltaics first, then on CO2 capture and drug delivery, and eventually in September 2014, I landed here in Swansea, where currently I'm working on carbon capture utilization with strong ties with industry. What I'm going to show you now in the next half an hour is these cherry-picked examples of work I've done. So the first one is from my PhD, where I developed sensors for nitrate detection in drinking water. The second one, I worked with photovoltaics, where you will see, I'll try to explain myself in a moment. I did some changes to make photovoltaics more stable than they are. In Rice University in Houston, I was lucky enough to collaborate, you will see, with people in the MD Anderson Cancer Center and develop a vector to treat pancreatic cancer. Actually not applied, but works in terms of delivering drugs, potentially. And finally, I will cover quite quickly what we have done recently in CO2 capture and utilization here in Swansea. These, and that's the reason of the title, efforts are aligned with the Sustainable Development Goals. We know there are 17. They are all listed there. And the one that are aligned with what I've done are these four. And you can see health and well-being connected to pancreatic cancer, clean water, this nitrate sensing system, and then we have renewable energy as affordable and clean energy solutions. And finally, the last one is about decarbonizing, making industry more sustainable. So these are my stops along the journey where I want to show you what I've done at different level of impact. Obviously, I shouldn't say obviously, maybe what you do in a PhD is not going to change the world, depending on how good you are. But I think eventually here in Swansea, we are picking up speed and potentially bring to fruition what we are doing in terms of also impact. So the first stop is about water. The Sustainable Development Goals says managing water and sanitation, so we have access, everyone, in a fair way to clean water. One of the issues with water is nitrates, pollution. So what nitrates are present in water normally, so they are present in nature, so they are normal present. However, if the amount of these nitrates is too high, there are issues for the aquatic body. You can see this hand dipped in water where there are a lot of algae. This is eutrophication. In present too much nitrate, algae overgrow and impede oxygen and light to enter in the water and kill the ecosystem. So it's necessary to control the amount of nitrate in the environment. And at the same time, we as people, we have to control the amount of nitrate intake because it can be harmful. You can see some numbers there of the limits of intake daily, but the number that I want to highlight for a slide in a moment is this 50 milligrams per liter, which is the limit of the amount of nitrate that can be present in drinking water. Here there shouldn't be more than 50 milligrams of nitrate per liter. Otherwise, it's not allowed to be sold. So what I've done, this is the first result, is to have developed an electrochemical sensor for nitrate detection. This electrochemical sensing is particularly interesting because it's simple to implement, differently from other techniques to measure this nitrate molecule. And what I've done was to use these materials, carbon nanotubes, metal nanoparticles, and conducting polymers, combine them in a working system that could allow sensing of nitrate. This is the paper that toward which everything converged during my PhD. And in order for you to appreciate, I hope, the quality of the results presented here and achieved, I have a very short tutorial here on the right-hand side for you to follow. Maybe it helps you to understand the data on the left-hand side. But here you can see the nitrate sensor. Obviously, this is a schematic. This pointing at the tip, okay, is where the composite I developed, I told you the components before, was placed. And what you do with the electrochemical sensor is to detect the electrical response in function of time, okay? You apply a voltage and you look for current to flow when the nitrate is inside the solution. So the nitrate is in this drop, okay? When I switch on the nitrate sensor in the absence of nitrate in solution, you can see now the current is 0. The drop goes in and the signal jumps. Another drop goes in and the signal jumps. Now this jump of current, no matter how simple it is proportional to the nitrate concentration. You build in this way the technique to measure the concentration of this pollutant and inside the water. So the outcome of this research was that this sensor that I developed comfortably could measure a limit of detection 25 times better than the legal limit from the one that I mentioned you before. And not only that, if you look at this data here, they are a bit noisy. It could potentially measure also hundreds of parts per billion of nitrate present in water. So this, on my side, in what year did I do it? 2011, wow, was my contribution in the area of clean water and in my journey to bring what I can do within sustainable development goals. The next stop is healthy lives and well-being. And in this case, I already mentioned to you that I've been working on creating and making vectors able to enter in pancreatic cancer cells. So just to justify this specific goal, this is one of the indicators of the goal. And the UK, specifically in this case, has probably call it a mandate is the wrong way to say it, but as a goal, a target of reducing the mortality rate of those diseases that you see listed there. So we have cardiovascular disease, cancer, diabetes, and chronic respiratory disease. You can see that the one with the highest mortality rate is cancer, unfortunately. And among all forms of cancers, pancreatic cancer is the worst. Okay, there is a reason. It's very difficult to diagnose, and the symptoms are difficult to, they don't really indicate that it would be a pancreatic cancer. And also treatment is not really effective. You can see from this data, from the Cancer Research UK, that pancreatic cancer is at the very bottom, and the net survival rate is the worst of all. So if someone unfortunately has this disease, has a 5% probability to survive. So what I've done here, very quickly again, when I was in Rice University, I met Ray Suzuki, who was working at the Texas Medical Center. It's the largest medical center in the United States with, I think, 100,000 people working there. And we met and we said, okay, can we use these materials here? They are very short nanotubes modified with polymers. Polymers will keep coming back to and see if they can enter selectively inside the pancreatic cancer cells. We embarked in this task. Before I go to the results, I want to show you what's the principle of this approach. Now, if you have a healthy part of the body, so normal cells, and you have nanoparticles like this nanotube with polymer attached to it running through the blood vessel, these nanoparticles cannot cross the blood vessel walls. Instead, it can cross those of a part of the body that has these cancerogenic cells, And by carrying a chemo agent, so a poison, this chemo agent can be delivered inside the cell and kill the cell. I have to say that in this work, we haven't really delivered drugs, okay? But we have proven that this molecule, depicted like this, can actually do that. So these fluorescence photos show two human pancreatic cancer cells. In the center one, the nuclei of the cells is stained for the purpose to see where the nucleus is, just for that purpose. And this red color instead is this nanotube, so this vector on which you would load the chemo agents to go in the cells, with a dye called the rhodamine B. The color of rhodamine B is red. So now, after I did these experiments, the fact that these cells, these cancerogenic cells, are red, show that the tubes actually entered inside the cells, and the overlap between the red and the nuclei, these vectors can also enter the nuclei of pancreatic cancer cells. The impact of this, the impact is this hasn't become a solution for the pancreatic cancer. However, later on, so this is a 2014 work, and these are 2022 reviews. This delivery system is mentioned as a handful, there are actually 3 here, of effective way to transfer nanoparticles within pancreatic cancer cell. And I believe, I'm sure, that many others have been working in this field, but just few are reported now in the literatures as successful way to deliver this. And this is another 2022 review reporting how these conjugates that I've made actually can enter the cytoplasm and the nuclei with ease. Okay, this stops here. If this was an impact presentation, I should show you also a company growing up, or I don't know how many patients I have saved. No, this stops here for now. Maybe somebody reading this would say, let's try it and bring it on, but that's it. But this is my contribution, and I'm really very, very proud of this, because later on I moved away from cancer, and I believe is an essential area of research that we all need to work in, but you need to take a decision in this pinball approach toward your career. Okay, third stop now is solar energy. I worked with solar. I see Matthew there. I'm happy that you're here, because I'm going to do a bit of a cheeky work where I worked in organic solar cells, okay? But here in Swansea, with specific, we are perovskites, right? But so I'm going to make a parallel between the two to show you that what I've done can be possibly transferred to perovskites, and we might want to talk about this after the presentation. Okay. So here I start with this incredible, beautiful graph that I will spend 1 hour to describe. No, I'm not going to do it. But I'm going to focus on the axis. Always when there is a graph, you want to look at the axis, right? Otherwise, how can you interpret it? We have cell efficiency. So this is the solar cell efficiency. It means how much in percentage of the solar energy coming to the cell becomes electricity. Okay, so the higher, the better. And these are the years where I started a bit later, have been working very hard to make this solar cell efficiency increasing over time, right? Now, there is a long list of possibilities and technologies. I am, if this works, singling out these two, as I just said, perovskite solar cells and organic solar cells. The reason is I worked in organic solar cells, but I'm just repeating myself, you'll see in a moment. Okay, so one thing to see is that at present, perovskites are better in terms of cell efficiency than organic solar cells. However, organic solar cells are very good in low light conditions, like in this room. If I had something that needs to be powered, I could have, I don't know, on my clothes, some organic solar cells powering this electronic device. And what the two have in common is that they both can be manufactured with roll-to-roll technology, and specific is in front of everyone in doing this. There are incredible papers coming up every single day. Probably every single day is too much, but I just saw one of the recent one, a fantastic one. Okay, so what have I done this here? I see at the moment it looks a little bit silly, but it's an interesting thing. Before I show you what I've done, here it is, a comparison between the two technologies, okay? Now, there are those games that you have to figure out the differences between two figures. You might want to try here, but to help, these are exactly the same things, except for what is called the photoactive layer. Okay, the photoactive layer is where the conversion, you need everything, by the way. You can't do just with the photoactive layer. But the photoactive layer is where, when the light comes, charges can be generated, okay? In one case, my case, I used what is called the bulk heterojunction. It's a mix-up, spaghetti style, of an organic polymer with an electron acceptor. Okay, we'll not go into details. On the other side, so this is a bit wiggly. The perovskite instead is a very ordered system of this kind with ionic species. They can be organic, inorganic, but that's the only difference. Okay, I mean, there's a big difference, but that's the only difference in these two architectures. There are many other architectures possible. What did I work with? I worked with these two parts, okay? This is called transparent conducting electrode, a whole transport layer, and you can see they are the same in both sides. And in particular, benchmarking of these two materials are ITO, indium tin oxide, and P.PSS. Who works in this area knows what they are, why they are there, for what reason. Just trust me, they are there, and they can be in both systems. So what I focused my research when I was in Houston, working with photovoltaics, was this coupling of materials, ITO and P.PSS. This is the work I've done. This published in 2013, so again, ages ago. You can see a cell here where the P.PSS are present where they were also before. I'm singling it out again, taking it out since that's the part I work with, and comparing it now with this polymer. It's called PPY-PSS. Fantastic. And then the difference is this PPY is called polypyrrole. Okay, this PDOT, I even don't know the name, so I should, but the fact here is that in making this substitution, that's what I've done first. Nobody has done it before, okay? It's probably something apparently silly. However, those working in the field knows that there are a lot of things involved into it, work functions, band alignments, morphologies, etc., etc. These worked out in this graph here, without going to the details. The curve represents the photovoltaic performance of the cell. Now, the fact that these two curves overlap each other, okay, show that I can substitute P.DOT with polypyrrole and the cell is still working. Good news, okay? But what's the point? The point is, and you can see it from this recent review, that one of the issues of stability of organic solar cells, but I believe also of perovskites and all other cells using P.PSS and ITO, is etching of the ITO, okay? So etching causes corrosion of the electrode and kills the cell, okay? This is not true. This is completely fixed when you put polypyrrole PSS, okay? You substitute this polymer, you remove the etching forever, and the cell is stable for a long time, okay? This is what I proved, and in terms of impact, I've been lucky, because when I searched for something to tell you, I found this paper. And incredibly, okay, this approach, 10 years later, has been applied in Korea, okay, in the University of Seoul, to make this high record efficiency organic solar cell for low light applications. They achieved, I think, 12% cell efficiency, but I was really very happy. That's why I'm highlighting it here, because that's my opportunity to do it, right? They say, okay, I did it, and they saw that the robustness of this system lifetime was greatly boosted by the less etching of the ITO. Okay, this again stops here. No, maybe they're going to make a company because there is already one here, Sensomedi. Good for them. I'm very happy to have contributed to this in terms of solar photovoltaics. I worked with this, I loved it, but then the pinball life brings you all around the place. I couldn't work anymore on there. I went and moved to work with the CO2 materials, and that's what I brought here in Swansea. I selected this goal. Typically, when you work with CO2, you always are connected with climate action, right? Okay, the word action is very specific. There is a lot to think about. Not that I prefer. I think that what I do is more about decarbonizing and defossilizing industry. So making the industrial infrastructure, okay, sustainable. That's why the goal is here. In particular, one of the targets of this goal is to, if you see there, to introduce, okay, upgrading the current infrastructure or retrofitting technology that makes industry more sustainable. And you measure this with this ratio, CO2 emission per unit of value added. What does it mean? The amount of CO2 that the manufacturing industry releases divided the wealth that the industry releases. So if you want to achieve this target, you have to maintain the industry very effective, making money, and at the same time, reducing CO2 emissions, so clean growth, right? How do we do this here in Swansea in our group? This is a scene where I try to squeeze in a slide all the work we have done in these 9 years. On the left-hand side, this is all about carbon capture materials and technologies, okay? On the left-hand side, I choose some papers that we published in using polymers. Can you see polymers? They keep coming back after going to Basel polyolefins. Using polymers to capture carbon dioxide. What does it mean, capture? I'm taking things, I'm assuming things. It means that industrial activity releases CO2 in mixture of gases, and when you capture it, you have to take it out from those mixture and let everything else go. So you need materials, sponges, to capture that CO2. That's what we do here. We make the sponges, okay? And yeah, we have worked with Heriot Watt, for example. Something I always love to highlight because I like the word positron annihilation spectroscopy. Okay, it sounds cool also. We use this in this paper in collaboration with the Idaho National Laboratory and also the Institute of Nuclear Physics in Poland. And also a prominent professor, if not the best, Christopher W. Jones from Georgia Tech was involved in developing this material toward direct capture, which is another area we work in, and there is not enough time. But this is just a flavor of what we have done. On the top here, this is to highlight that we also work with the family of material that is called metal organic frameworks. And this F4 MIL 140 cerium is a metal organic framework that we scale up here. And I have a very strong feeling that in parallel, if you know the area, there is a CALF 20 that is becoming the key material for carbon capture. This is following CALF 20. It's not only my work. Marco Taddei was involved into this, but we scaled it up here in Swansea. So we had to be, once this material will become important, we took our part. And finally, before moving to utilization, I'm not sure how much time we have, but I know that Ben took extra 10 minutes, so I probably do the same. This is a PSA unit. What does it mean, PSA? Pressure swing absorption, okay? So what this is, first of all, I have to tell you what we've done. We have designed it here in our team. I led the work package. Then we commissioned the build with all procuring of the parts. And then we deployed it in Rockwell. Rockwell is half an hour drive from here. And the unit now is inside the container here, and we are testing it to to decarbonize the emissions of their manufacturing process. And pressure swing is when you apply, you use changes of pressures up and down with inside these tanks, I hope you can see them, sorbent materials. The materials are not these materials because they cost a fortune, but commercial materials. And this is work we have done within the Reich initiative in Esri. And I think it was fantastic. Many other outputs came from RISE, but I'm really happy to show you that we also achieved this with currently testing in industry with the potential impact in decarbonizing and de-risking the application of PSA in decarbonizing manufacturing processes. This is the last part of the presentation, but this is the one that I'm most attached to, and is carbon dioxide. I didn't say it before, but I know that is common knowledge, is the cause of global warming. Carbon dioxide in the air traps heat. The heat melts the ice, etc., changes the climate. So there is so much carbon dioxide in the environment, in the air at this point, where although we have to remove it, we should also use it instead of trying to hide it somewhere, right? And that's what we are trying to do, to find ways to use carbon dioxide. So we want to take carbon dioxide, converting it into something useful. That's utilization, making something useful out of carbon dioxide. Now, something useful to do is ethylene. Well, we could have an argument, if not, I don't know, a kickboxing match here, because some people hate ethylene because of microplastic, etc., but it's a long conversation. One aspect that no one should argue with is that ethylene currently is made on a very large scale, 200 million tons per year, with a corresponding emission of 400 million tons. If you compare it to the global emission, is more than 1% of global CO2 emission. Okay, so how can you address this issue? One is if you use CO2 to make this ethylene, trust me, this C2H4 is ethylene, okay. To make those 200 million tons of ethylene, you would be using 600 million tons of CO2. And that's a big dent in the emissions, right? In this almost 40,000. There are many options to do it. My option, because of my pinball trajectory, okay, was to apply electrochemistry. Now, this is brutal what I'm going to say now, because the things are much more complicated than I'm going to show you in a second. But what is it, CO2 electrochemistry? It is this, okay? You take CO2 from emissions, for example, you extract the CO2, you mix it with water, you stick in electricity from the plug, and then if you have the right technology, you need electrolyzer, electrodes, and catalysts, we do all of them here, you can make sustainable chemicals, including ethylene. You can make it using CO2 from manufacturing processes. This is called decarbonization. This is another story. But you can also use CO2 directly extracted from the air. So you have a nice big filter. You draw air through it. The filter captures the CO2. And then you use this CO2 to make the ethylene. And this is called defossilization because you remove fossil carbon from the process. So here, this is a pioneering work, I would define it. We did here in Swansea, where we proved that if you take a metal, these orange balls here, spheres, okay, and you mix them with a polymer, these things on the top, you can facilitate conversion of CO2 to ethylene. Okay, then again, the story is very, very long and complicated. The funny part of this is that I did this work with my first grant, and the goal of the first grant was to make methane. So I ended up doing ethylene, but it was better than methane, so that's good. This work involved international partners, but also the synchrotron. We went to do in situ characterization using synchrotron radiation, and the synchrotron highlighted this in their best output of the year in terms of contribution to CO2 conversion. What happened later on then, I'm always having troubles reading. So Gertz, okay, the professor of University of Illinois Urbana-Champaign, used a similar approach. You can see it here, where there are, again, the orange spheres and the polymer, holding amines like in our case, but using a gas diffusion electrode, which is a particular technology. But what I want you to see is that using a similar approach, he achieved very, very high CO2 to ethylene conversion, up to 90%. This opened up the direction toward effectively doing CO2 to ethylene conversion, okay? GDEs, at the same time, in 2020, was an area where we entered also. These are two review papers that we published, all connected to gas diffusion electrodes, including one on applying a technology where GDE is commonly applied on a very enormous, incredibly large scale. It's a chloralkali technology where electrochemistry is used on an enormous scale. We want to transfer this technology into CO2 conversion. This is what Craig is doing. The fact that there is only the photo of Craig is not because I don't prize everyone. There will be an acknowledgement picture slide at the end, and I am grateful for everyone who has been involved. It's just, this is just on time, as it happens, work. And what we are doing is to develop these electrolyzers where we implement this large-scale technology. This schematic shows a rendering of a system that is already in the lab right now, and we have already achieved significant advancement in the stability of this gas diffusion electrode, which is the first step in doing this. Funding is coming from Sustain, and this is work where we work with UK steel makers to decarbonize their processes by using CO2 from steel making to make steel greener. And this is just the last slide. I'm extremely happy to say that we have partnered also with the Coca-Cola Euro-Pacific Partners Ventures. We received funding for this project, AirTops. It's a super incredible, ambitious project. That's why it's a venture investment, where our goal is to take CO2 directly from the air, okay, with other technologies that Coca-Cola is sponsoring, convert CO2 to ethylene, what I hopefully gave you an idea in the previous slide, and from there, with the known technologies, polymerize it and make bottle tops. Now, if you go to buy a Coca-Cola bottle, the bottle is made of PET, but the top is made of high-density polyethylene. So they want to make sustainable high-density polyethylene by making it from CO2 instead with the steam cracking from fossil carbon. The potential of this in terms of impact is enormous. So these are the packaging I want to read the word that is written here. Represent the number of packages introduced by Coca-Cola Pacific Partners in 2022 in 1 year. You see there are 11 billion bottles, so 11 billion bottle tops that could be decarbonized. Altogether, they are 35.5 billion, but some are made of other materials. When these came out, there is already some attention from the media, where you can see that Swansea University now is working with Coca-Cola to decarbonize and make their packaging more sustainable. And this is the very last part, from a press release of Coca-Cola. And the reason why I'm putting it is, again, to try to stress the importance of what we are doing and the level, okay? This is the second partnership they choose. The first one is the University of California, Berkeley. And there, they're doing an abiotic, non-biological, synthetic conversion of CO2 to sugar, whilst we are working on converting CO2 to ethylene. With this, I conclude the journey into my contributions to these sustainability challenges. And I want to thank you, everyone, okay? I want to thank the faculty for all the support I received, all the Department of Chemical Engineering, where I'm serving, I like the word serving, as a head of department. With your support, everything is possible. And everyone involved in Swansea University, those that were involved in the past in my random way of moving toward the industry, the academia, etc. All group members that have been involved in all this work, present and past, collaborators, and all those that have been so kind to provide funding for this research to proceed. Thank you.